Mathematicians love to explore the relationship between an algebraic equation and its geometric graph. For example, what happens to the graph when the equation is multiplied by 2? Hi, my name is Tom Atwater, and we will be investigating just that, how algebraic changes to the equation affect the graph. Let's start by discussing vertical stretches. We're going to look at 4 different graphs. The basic graph of y equals x squared, and then we're going to look at y sub 2 equals 2x squared, 3x squared, and 4x squared in order to do this investigation. What we're going to do today, though, is we're going to use some software that's on the computer. So let's go to the graphing calculator that's on the computer, and we're using some emulator software, which is going to show us the TI-84 calculator on the computer screen. So let's take a look. On the far left side of your screen, where you can see the mouse moving a little bit, you see a TI-84 Plus Silver Edition faceplate. I want to remind you that the TI-84 Plus and the TI-83 Plus are exactly the same in terms of both the window for the output that I'm circling here, as well as the entire keypad that I'm circling here. They are both the same. So everything we do today using this emulator software applies to both the TI-84 Plus and the TI-83 Plus. What I want to show you, though, is we're not going to be looking at this faceplate that often today, but instead we're going to use 2 other features of the emulator software. This window here called the large screen, that is a blown-up version of the output window of your TI-83 Plus or your TI-84 Plus. Over here, on the right-hand side, I have done each of the different examples that we're going to use today and created the keystrokes that will help you to follow me along as I punch those keystrokes into this emulator software. Okay, so let's do our first example using the graphing calculator emulator software on the computer screen. So our first example, I've got all the keystrokes over here on the right, so this is how you can follow along with me, and I will do them each one by one. So the first key to hit is your window key, and that'll bring up this window where you can set your minimum and maximums for both x and y. So the minimum for x is going to be -5, so we'll plug that in. Then we'll move down to the maximum for x, which is going to be 5, so key that in. Then we need to move down twice, because we're going to leave the x scale the same, and for the minimum for y, we want to enter -5. Then we need to move down to the max for y and enter in 20, and we're going to leave the resolution and the scale for x and y to be the same. So the final thing you want to do is on your keypad is hit the graph key. I'm sorry, hit your equation key so that we can enter the equations. So the first equation we're going to enter is the x key followed by the x squared key, so y equals x squared. Then we'll move down to y sub 2 for the second equation, and this time we're going to enter 2 key, then the x key, then the x squared key. For our third equation, we move down to y sub 3, and we're going to hit the 3 key, and then the x key followed by the x squared key. So we have 3x squared. Then we're going to move down once more to the y sub 4 equation, where we will enter 4, followed by the x, and then the x squared for y sub 4 equals 4x squared. Now we hit the graph key, and we will see y equals x squared get drawn right there. Here comes y equals 2x squared. Then y equals 3x squared. And it finishes off with y equals 4x squared. And what you'll notice about this is that when each of those graphs was drawn, the graph became stretched in a vertical manner compared to the original graph, which I'm circling here, y equals x squared. Each one of these graphs was stretched vertically compared to this. So let's summarize what happened when we changed the coefficient of x squared to 2, 3, and 4. And what happened is that the graph of x squared got stretched vertically. So now what we want to do is summarize that. Let's put it in writing what it means to do a vertical stretch for the graph of a function. Vertical stretching of the graph of a function. If a point xy lies on the graph of y equals f of x, then the point x, comma, cy lies on the graph of y equals c times f of x. If c is greater than 1, then the graph of y equals c f of x is a vertical stretching of the graph of y equals f of x by a factor of c. Let's take a look at an example of this. We have a graph labeled y sub 1, which is f of x equals the absolute value of x. We have three other graphs, y sub 2, y sub 3, and y sub 4, which are defined by 2.4 times the absolute value of x, 3.2 times the absolute value of x, and 4.3 times the absolute value of x. And we're going to determine the correct equation for each graph. So our basic graph is for the equation y sub 1 equals the absolute value of x. And that's this graph right here. Now, what we just learned is that when you put a coefficient in front of the absolute value of x, we're going to get a vertical stretch. And the stretch depends on the size of your coefficient. So for this first one, y sub 2, that actually is going to be 2.4 times the absolute value of x. And the reason for that is this one is the one that has been stretched a little bit more than the original, but there are two other graphs that have been stretched even further. When we take a look at that middle graph right here, we would have to take the equation that has the middle-sized coefficient. In other words, 3.2 times the absolute value of x would go for y sub 3. And then finally, of course, the 4.3 times the absolute value of x, that's going to equal our y sub 4. So that's how you would match those up. Now, let's take a look at another type of stretch. Let's take a look at what happens when we use coefficients like 3/4, 1/2, and 1/4. And let's take a look at how those graphs compare with the original graph of just y sub 1 equals x squared. All right, so let's take a look at this on the graphing calculator. Over on the right-hand side, I have the keystrokes that we're going to follow. The first thing I want to do is click on the window key to make sure that our window is set up, in which it is. We want a minimum maximum values of x of -5 and 5, and for y, we want a minimum value of -5, and for y's maximum value, we want 20. So the next key to hit is your y equals key so that we can enter the equations. Now, the first equation is left over from before, and it is correct. So it's y sub 1 equals x squared. We'll move down to y sub 2, and what we need to type in there is the 3 key, followed by the division key, followed by the 4 key, then your x and x squared keys. Remember that your graphing calculator follows the order of operations, which means it's going to do 3 divided by 4 first, because it comes in that order, and then that's going to be multiplied times x squared. Therefore, you don't need to use parentheses. Let's move down to the third equation, where we need to enter in a 1 divided by 2, and then our x and x squared. Then move down to the fourth equation, y sub 4, where we'll enter 1 divided by 4, x, and then your x squared key, and then you want to click on your graph key. So it first graphs y equals x squared. Next, it's graphing y equals 3/4 x squared. Then y equals 1/2 x squared. And finally, it's going to graph y equals 1/4 x squared. And so what's happened in this particular case is you will notice over here on these graphs, this graph being the y equals x squared, each successive graph actually got compressed towards the x-axis. That is, it shrunk down. So let's summarize what we've just learned. When we have a coefficient that is a fraction, a number between 0 and 1, what happens is the basic graph gets compressed, or it gets shrunk towards the x-axis. Let's formalize this and put it in writing, what it means to have a vertical shrink of the graph of a function. If a point x comma y lies on the graph of y equals f of x, then the point x comma cy lies on the graph of y equals c f of x. If c is between 0 and 1, then the graph of y equals c f of x is a vertical shrinking of the graph of y equals f of x by a factor of c. Let's do an example of this. Let's take the graph which we have labeled y sub 1, and that is the function f of x equals x cubed. Then we have three other graphs along with the equations defined by 0.5x cubed, 0.3x cubed, and 0.1x cubed. And we need to determine the correct equation for each of these graphs. So our basic graph is y sub 1 equals x cubed, and it is this graph right here. And then what's happened is we have that graph being compressed towards the x-axis, giving us these other three graphs here. Let us start with y sub 4 and realize that's been compressed somewhat. That is to say that it hasn't been compressed as much as the other two graphs, and therefore y sub 4 is going to be equal to the 0.1 x times x cubed. Then when we take y sub 3, that one's been compressed a little bit more, but not the most, and therefore y sub 3 goes to 0.3 times x cubed. Let's explore horizontal stretches and compressions. We have in front of us three functions, which are defined by y sub 1 equals f of x, y sub 2 equals f of 2x, and y sub 3 equals f of 1/2 x. We're going to graph these and check out how each graph compares with the original y sub 1 equals x squared. To do that, we are going to switch over to our graphing calculator software. So let's take a look at that. We're going to call up the keystrokes for those three graphs, and here they are over here. And again, I just want to double check, and you should always do this because you're never sure what is in the window, and we want to make sure that the window has the same settings which it had before, so it does. And so now we can, no, actually we do want to change these settings. We want to change them, and so we're going to move down and change the settings for the minimum for y to be -10. And then move down for the maximum setting for y to be 10. Now we can click on our y equals key so that we can enter the equations. And the first equation that we want to enter is, of course, y equals x squared. Then we move down to y sub 2, and we're going to enter in, first I cleared that out, and now we're going to enter in 2 times x in parentheses now, and then the squared key because we want both 2 and x to be squared. Let's move down to the next equation, y sub 3, and first I'm going to clear that out of there. We're going to put in the parenthesis. We're going to then put in 1 divided by 2, then times x, close the parentheses, and raise that to the second power. I'm not interested in y sub 4, so let's move down there, clear that out of there, and now let's click on our graph key. So the first graph we get is y equals x squared, then we get y equals 2x squared, and finally here comes y equals 1/2 x squared. So what you'll notice this time is that these graphs either were compressed or stretched in a horizontal manner this time. Horizontal stretching or shrinking of the graph of a function. If a point x comma y lies on the graph of y equals f of x, then the point x divided by c comma y lies on the graph of y equals f of cx. If c is between 0 and 1, then the graph of y equals f of c times x is a horizontal stretching of the graph of y equals f of x. If c is bigger than 1, then the graph of y equals f of c times x is a horizontal shrinking of the graph of y equals f of x. Let's take a look at an example of this. Let's say we're given the graph of y equals f of x, and it's this graph to the right-hand side, and we're going to be asked to graph y equals f of 1/2 x. We have three distinct points on here that are going to help us to locate our new points of the graph. And so let's take a look. What we have is the new graph down below, y equals f of 1/2 x. And what you'll notice is that we got what we expected, which was a stretch horizontally of the graph. And what I want you to notice is the 2 points I've circled are, of course, twice in terms of the x coordinate what they were before, but the y coordinate has remained the same. And therefore, when we look at the y-intercept here, what you realize is, of course, doubling 0 leaves it at 0. So the y-intercept doesn't change when you do a horizontal stretch. All right, the next thing I want to do with you is to discuss reflections. So we're going to take a look at what happens when we have two functions defined y sub 1 equals f of x and y sub 2 equals negative f of x. So in the first set A, we have y sub 1 equals x squared and y sub 2 equals negative x squared. So once again, what we'll do is we'll switch over to our graphing calculator, and we will bring up the keystrokes for y equals x squared and y equals negative x squared. But this time we do have to work with the window and make some changes. So click on your window key. We can leave the x minimum and maximums the same, but I want to go back to the y minimum and change it to -5, and the y max we're going to change to +5. Now click on your y equals key, which will bring up this screen, and then the first thing to do would be to clear out that and then enter in our first equation, y equals x squared. Then go down to y sub 2, and this time we're going to clear that out and enter negative x, and then the function y sub 1. Now, what am I doing here? What I'm doing here is this is a shortcut so that what happens is y sub 2 is simply going to be the negative of whatever y sub 1 is. And in this case, it'll go back and say, oh, y sub 1 is x squared. Keeping on, I want to clear out the y sub 3 equation because that's not part of what we want to graph. And now we can click on the graph key, and there's y equals x squared, and here comes y equals negative x squared. What you see happen there is that we had a reflection of the original graph across the x-axis. And so it ended up going across the x-axis, and we have it now below. Let's graph set B now. So let's click on our window and make sure that that's still set up, which it is. Now click on the y equals key so that we can enter our equations. We need to clear out x squared, so click on the clear key, enter x, then hit the math key, and then the number 3 key, which will give us the cubed. So we have y equals x cubed. Down below on y sub 2, I could leave that as negative y sub 1. However, I want to go over the steps of getting the cube for you. So we'll clear this equation. We'll type in the negative. We'll get the x. And now here's how you get the cube. You click on the math key, then the number 3 key, and that gives us our x cubed. And finally, let's graph them. Here's our original y equals x cubed, and here comes the y equals negative x cubed. So once again, what you'll notice there is that we got a reflection across the x-axis. Well, that's a reflection across the x-axis. Now what I want to do is look at another type of reflection. So we're going to look at a couple of examples and discuss what they would look like in terms of the graphs of the equations so that we can see what a different type of reflection will look like. So this time we have two functions defined by y sub 1 equals f of x and y sub 2 equals f of negative x. In our first example, C, we have y sub 1 equals the square root of x, and then y sub 2 equals the square root of negative x. Once again, let's switch to the graphing calculator software and call up the keystrokes for entering those two. So let's step through this. Let's just check the window out and make sure it's all set, that we have our minimum and maximum. Now our equations. We're going to clear out x cubed, and this time we're going to enter in the second key followed by the x squared key, and that gives us the square root key. Now we put in x. You don't have to put in a parenthesis now, although you can put in a parenthesis, but it understands even without the parenthesis that you have y sub 1 equals the square root of x. Let's move down to y sub 2 and then clear out that negative x cubed, and this time let's enter the way that I showed you before, the variable, then hit your the right hand move key, then the enter key, which is going to allow us to take y sub 1, and then we want to put in negative, the parenthesis with a negative, and then x followed by the parenthesis. So we're taking advantage of the graphing calculator's ability to do functions. So this is telling us the function y sub 1 of negative x. Let's graph it and see what happens now. So click on the graph key, and the first thing it does is graphs y equals the square root of x, and here comes y equals the square root of negative x. And what it looks like to me happened there is that we got a reflection across the y-axis this time. Let's take a look at the second set of equations and graph those. So once again, here are my keypads. I'm going to click on the window key, double check that it's set up correctly. It is. Now click on my equation key, the y equals key. I need to clear out the equation there, and now I need to enter in the cube root. And the way we do that is we click on the math key, the 4 key, which will give us cube root, and then I put in x plus 4, close the parentheses because I want to take the cube root of that whole expression, x plus 4. Let's go down and realize that we can just leave the y sub 2 equation just as it is. That is to say, in function form, use y sub 1 of negative x. Let's graph this, and the first thing it graphs is y equals the cube root of x plus 4, and so that's the x cubed shifted to the left 4, and here comes y equals the cube root of negative x plus 4. And what you'll begin to see is that, once again, this is a reflection across the y-axis. And so, in summary here, what was happening is when we replaced x with a negative x, we got a reflection across the y-axis. So let's formalize this in writing and take a look. reflecting the graph of a function across an axis. For the function y equals f of x, we have A, the graph of y equals negative f of x is a reflection of the graph of f across the x-axis. And part B is if we have the graph of y equals f of negative x, that's a reflection of the graph of f across the y-axis. Let's take a look at an example. We're given the graph of y equals f of x, and it looks like the graph we have right in front of us. We wish to graph the two functions y equals negative f of x and y equals f of negative x. So for part A, we know that we're going to, both of these are reflections. For part A, we're going to have a reflection over the x-axis, and for part B, a reflection over the y-axis. So let's take a look at both of those. What we'll notice is that for A, we have each of the points that used to be above the x-axis on the original graph are now shifted across the x-axis. That is, they've been reflected. Notice that our x-intercept, y-intercept, which is right at the origin in this case, doesn't change. And then this point, which originally was below the axis, is now above the axis. All right, then for y equals f of negative x, what we have is, of course, a reflection across the y-axis. So everything that used to be on the positive side of our y-axis is now on the negative side. And everything that was on the negative side of the y-axis has been shifted over to the positive side of the y-axis. So those are examples of our reflecting across the axis. What I'd like to do next with you is explore what are called multiple transformations. That is to say, we're going to combine the different kinds of stretches or reflections or shifts that we've been looking at today so that we're doing more than one of them at a time. So let's take a look at combining multiple transformations. To determine the order in which you combine the transformations and in the order in which they are made, you use the order of operations. So let's look at an example of this. Describe how the graph of y equals -3, parentheses, quantity x minus 4 squared plus 5 can be obtained from the graph of y equals x squared. And then sketch the graph. Okay, so we have a few things happening here. If we start with our original equation, we can see that one of the things that's happened is we subtract 4. And since that's in parentheses, we have to do that first. And that means we're going to shift it to the right 4 units. Then we have this negative as well as the 3. And I'm going to deal with those separately. The negative, remember, is a reflection across the x-axis, and the 3 is going to be a vertical stretch. Again, those are what follows in the order of operations, and then the final step is the plus 5, which means it's a vertical shift of 5 units. And let's take a look now at what that would look like for each of those. Okay, so we have here the shift right. So what's happened is normally y equals x squared goes through the origin, so it's been shifted 4 units. Then we have the vertical stretch of the 3, which means it's been stretched this direction. Then we have the reflection across the x-axis because of the negative. So, of course, everything that was up goes below. And then finally, we have to take this graph here and shift it up 5 units because of the plus 5 there. All right, that's great. That's an example of combining a lot of transformations into one. Well, now it's time for you to try a problem. Give the equation of the function that would be obtained by shifting the graph of y equals the absolute value of x 3 units to the left, vertically shrinking it by a factor of 2/3, reflecting it across the x-axis, and shifting it 4 units downward in that order, and then sketch the graph. Pause the video to work on this problem, and when you are finished, restart the video to check your solution. All right, let's find out how you did in this problem. Let's take a look at the solution that I've come up with, and you can check to see if you have the same thing. So here we have. The first thing we had to deal with was the shift left of 3 units. And so we have here, the shift left is x plus 3. Then we had the vertical shrinking of 2/3. We had the reflection across the x-axis, and then finally a shift downward of 4 units. So that's how your equation should look, and then your graph would be this graph right here, where the point that used to be at the origin is now at -3, -4. And just in terms of the y-intercept, you would have that at 0, -6. So that's what your graph should have looked like. So in this lesson, we explored transformations. Be sure to work the exercises that your teacher assigns, and we'll see you next time.